Hey everybody, welcome back to Unit 8 for Electricity and Magnetism of AP Physics C. So today we're going to kind of keep talking about these concepts of electric fields. In the electric fields video, the last one, we were focusing on point charges. So now what we're going to look at is just different charge distributions. This is a very common question. This is where they like to do the derive an expression question. It'll be a multiple choice, it'll be a free response, but it'll be different configurations of charges. So what happens is the expressions for the electric field of specified charge distributions can be found by using integration and the principle of superposition. So this is a section where calculus will run right into it. And so what you're going to do is use the equation E, right? So that's our electric field, is equal to 1 over 4 pi epsilon naught. Well, that's just simply K. The integral of dq, should be a lowercase q. I'm trying to stay consistent with what you would see on the formula sheet. So dq divided by r squared, right? And then because this is a vector, we have to introduce in our unit vector notation, which is that r hat notation. Now, what makes some of these questions a little bit easier is if there's symmetry involved. Okay, so you can use symmetry considerations to simplify the analysis of the electric field. Okay, now what are some of these common distributions? Right, so you have two wires, you have an infinite wire, and then you have a finite wire. So infinite wire is a really long wire, and what that allows you to do is not worry about any contributions from the ends of the wire. And then a finite wire where you would have to factor in those ends. You would have kind of a semicircle, right, or an arc, because with it may just be a simple semicircle, but also they may not give you the full semicircle, give you like a quarter of a circle. And then the last one is a ring of charge. Okay, where you're looking for a point that is on an axis through the center of the circle. And remember, so with all of these, you're going to look for at certain points. They're going to say like at point P. What is the deriving expression for the electric field at point P, right, for this distribution? So let's look at an example problem. So here in the example, we're going to do the ring of charge. So it says derive an expression for the electric field at the center of a ring of charge with a radius A, right? So the ring has a radius of A and a distance point P away from the center. So something to note, X, and sometimes I call this R, but this square root of X squared plus A squared, they're going to be constant, right? So is the radius of the circle. So everything that is indicated there, those are going to be constant. So in an integral, if you have to use, something, if you see that running around in there, you can just simply pull that out because it is a constant value. So if we're looking at point P, something you'll notice, like there'll be an electric field here, field here, field here, right? So you have like these infinite amount of fields caused by this dq, right? So the dq is just all the infinitely small bits of charge. Okay, that's what we're going to integrate through or about. Okay, and then what you'll see is like here, right? There is a positive y component and a negative y component of the same size. So what happens is all the y components will cancel and only leaving the x components. So we're not necessarily going to integrate through y, we're going to integrate through x. So we want the net electric field, right, is going to be, in this case, simply E sub x. And what does that mean for us? It's going to be E cosine theta. And for us to, if we think about like that would be kind of standard. So if we're going to look at, and we have an infinite amount of these little pieces, right? We're going to do the, say dE dx because the E field is going to change, right? And that's what we're going to kind of look for. So we're going to say is Ex is going to be equal to 1 over 4 pi epsilon naught, okay, integral dq over r squared. Now, we can take care of this cosine theta, all right, by simply, knowing the ratio for cosine. It's adjacent over hypotenuse. Well, x is your adjacent. This root x squared over 8 plus a squared is your hypotenuse, right? And so that's going to kind of be what that's going to factor into our r, okay? So we're going to substitute in x over square root x squared plus a squared for cosine theta, right? But the distance are going to be away, right? And so we would have this cosine theta factor running around in there as well. Okay, the distance that they're going to run around is, r squared. So every piece is going to be separated by that r value. Okay, so r is our hypotenuse in this case. So we can separate, this right here is our r. And so I can put that in. So what happens is a lot of these just end up being kind of like substitution type problems. So we would have 1 over 4 pi epsilon naught integral of dq over square root of x squared plus a squared times x over square root of x squared plus a squared. Well, right? Constant. So we can pull all that out. So we end up with x over 4 pi epsilon naught times square root of x squared plus a squared, right? In fact, we can do a little bit of simplifying, right? So this ends up canceling. So you have x squared plus a squared. And then this is to the 1/2, right? If I rewrite it. So that's like 1 plus 1/2, which is 3/2. Sorry, I keep going back and forth with big Q and little q. So this actually makes it very simple because now our integral is just q, right? So the integral of dq. Well, this d, integral cancels that d. And so the expression for a ring of charge at a point, in this case, p away, would be qx, sorry, I put k, over 4 pi epsilon naught parentheses x squared plus a squared to the 3/2. Okay, so this is the expression for the ring of charge. All right. Now, in the next video, we're going to move past rings of charge, and we're going to look at electric flux, which then leads us into the last part of the unit, which is Gauss's law.